Alright, good evening guys. Here we go. Here's 10.2. Updating the slides and giving you guys a little video of this. If you join, I'll be checking. We could actually ask questions live. And I think I have the audio component down so you guys can hear me and we could have a little conversation about the lesson going on. Alright, so here we are again. So we did 10.1 yesterday. Again, if there's any questions on homework, let me know. A couple more definitions in this unit. The central angle, which I think we've spoke about before, and the arc here. And if angle AOB is less than 180, then the circular arc is called the minor arc, denoted by arc AB. Alright, so that is called the minor arc. Alright, so let's see what we got here. So we have the central angle, we have the minor arc, and then with the minor arc comes a major arc. Okay, so arc AB is the minor arc, and arc ADB, so ADB going all the way around, is the major arc. Easy enough, I think. Semicircle, just half the circle, no big deal. Alright, let's see what we got. Measuring the measure of a minor arc and the measure of the major arc. Please recognize that a whole circle is 360 degrees. Alright, so if the minor arc is given to you as 50, then the major arc of a dB going completely around the circle is going to be 360 minus that, right? So the 310 and the 50 will make up the 360 degrees. Alright, nothing too crazy. Finding the arc measures of arcs. Alright, nice and easy. RS, the minor arc, is 110. Alright, so we have a couple options here. So notice that RT is the diameter and given. So that means the arc from here to here. So this is going to be 180 degrees, which is the diameter, or half a circle. So that means this is 70 degrees. These two are. So RTS is 70 degrees. RS is 110. Together TSR is 180. And then what is that? What else is asking for? RST 180, 180 degrees. RTS, I'm gonna do this one in green. RTS going all the way around. All right, from here to here. So again, the whole circle is 360, and we'll take away the minor arc of RS, which is the 110, and that gives us our 250 degrees. And again, 250 and 110 will give me a total of 360. Alright, so far so good. Take a moment to digest all this so far. And let's see what our next example is here. Alright, so I think we got another definition here. Two arcs of the same circle are adjacent arcs. Two arcs of the same circle are adjacent arcs. Where when they intersect at exactly one point, you can add the measure of the two adjacent arcs. So arc addition postulate. The measure of an arc formed by two adjacent arcs is the sum of the measures of the two arcs. Alright, so here we go. Arc, the measure of arc ABC. So ABC. So A, B, C. This entire arc, right, is made up of two arcs. Made up of the arc AB and the arc of BC, right? So you've had segment addition postulates, now you have arc addition postulates, right? Same concept. All right, so a couple extra examples here. Let's see what we got. I'm gonna pause for a quick second. All right, so just making sure nobody else was on. So we arc GE, GEF, and GF. I'll do GE in red here. So G is from here all the way to here. So this is arc GE made up of, so arc GE is equal to the arc of GH and plus the arc of HE. So we got 40 plus 80, giving us a grand total of 120 degrees. Alright, so now that we know this is 120, then we got arc GEF. So going blue, G, E, F, going all the way through. So we got 120. So we got GH, HE, and FE. So GEF, we have 120 degrees for this piece, and then 110 degrees for FE, and that gives us a total of 230 degrees. And last but not least, we'll go in green here, arc GF. Alright, well, if you know the entire thing is 230, then this is going to be my 360 minus 230, giving me a total of 130 degrees. Alright, for arc GF. Alright, so a couple addition and subtraction problems, nothing too hard yet. Alright, bringing us to example 3. A recent survey asked teenagers whether they would rather meet a famous musician, athlete, actor, inventor, or another person, and the circle graph shows the results. Alright, and who would you rather meet? Alright, so the measure of arc AC, let's see where AC is. Here's A, here's C, going all the way around. So measure of AC, we have 29 degrees plus our 108 degrees, giving me a total of 137 degrees. Mark A, measure of ACD. So ACD coming from here, A, C, and D, stopping here. So we have ACD, so we'll be here. We got 29 degrees, 108 degrees, and including the CD, which is 83 degrees on this one. Alright, and that gives us a total of 220 degrees. Alright, and that's part of doing part B. And then let's see what else we got. We got measure of ACD, measure of ADC. So ADC, so we're going to go backwards this time. So ADC goes all the way around this way. Alright, so part C. So just be careful for your orientation. ADC, so we have 79 degrees. That's this piece from A to E, plus another 61 degrees. E to D, and then D to C is got another 83 degrees there. 10, 3. This will give me a total of 223 degrees. And last but not least, we got one more color here. We got D, measure of arc EBD. So here's E, B, and D. So this is going completely all the way around. So rather than adding all these, I'm going to look at arc EBD going completely around. So it's almost the full circle, except I'm going to subtract the ED part that I don't have. So it looks like we're having, it looks like that measure is going to be 299 degrees. Alright, so here's definitely a couple examples you could try on your own. Alright, TQ, you could do this. I'll just write the answers up here. Give it a shot. TQ is 120. This one's going, QRT is going to be 240. TQR is going to be 180 degrees. QS is going to be 160. TS will be 80, and RST is 180 as well. RST giving you a semicircle. All right, and major arcs and minor arcs. All right. So again, a minor arc is less than 180. A semicircle is 180, and between 180 and 360 is a major arc. All right, a couple definitions there for you, and that, for the most part, is 10.2. We have a few more theorems in here, all right, and then we'll wrap this one up as well. Alright, so 10.2, we got two circles are congruent if and only if a rigid motion of composition of rigid motions maps one circle onto another. The statement is equivalent to congruent circles theorem. Two circles are congruent circles if and only if they have the same radius. Okay, easy enough. So congruent circles, they have the same radius. Alright, and here's another congruent central angles theorem. In the same circles or in congruent circles, two minor arcs are congruent if and only if their corresponding central angles are congruent. So pretty much if you make a set of vertical angles, then these two angles are congruent if the arcs are congruent, or if the arcs are congruent, then the angles are congruent. Alright, going either way. Alright, so let's take a look at what kind of examples I can give you on this one. Alright, so tell whether the red arcs are congruent, explain why or why not. So angle CBD is a central angle. Let me use a different color there. Angle CBD is a central angle. EBF is also a central angle. So arc DC is going to equal 80 degrees, which is also equal to EF. I'm on the second example, example 4 here. I'm on part B. Tell whether the arcs are congruent or not. Alright, so here's arc RS, which has a central angle of 90 degrees. And then you have arc TU, which shares the same central angle. So are the arcs congruent? And they are in fact congruent here because they share the same arc. So arc RS is equal to 90 degrees, and arc TU is equal to 90 degrees. Therefore, these two arcs are in fact congruent. Alright, and then the last one is UV. Tell whether the red arcs are congruent again. So is arc, that looks like VV. So is arc UV congruent to arc YZ here? Alright, again, the arcs are congruent if the angles that they construct are equal. Right? If the central angles are equal, then the arcs, so DC is equal to 80 degrees off the central angle, EF is equal to 80 degrees off the central angle, RS is 90, TU is 90, UV is going to be 95 degrees, right? And YZ, again, this is the same triangle, is also going to be 95 degrees. Therefore, also congruent. Alright, so let's come back and adjust B. So RS is the 90 degrees angle. TQU also uses the 90. RS has a different radius than QT. Right, so the radius for RS is not the same as the radius for QT. So these arc lengths are not the same, so these are not congruent. But the arc does make 90 degrees of, RS is 90 degrees of the circle, TU is 90 degrees of that circle, but still those two lengths are not congruent. Right? A is all part of the same circle. C, the indication here was that TV is congruent to XZ, so therefore they have the same radius. If they have the same radius, then the circles are the same. If the circles are the same, then the arc, the 95 degree arc, will give you a arc length of UV congruent to an arc length of YZ. Right, where again in B you do not have the two same circles. All right, and then last one here, we have two examples here. Tell whether the red arcs are congruent. Indication that these two have the same radius, so therefore the arc AB is going to be congruent to arc CD. They both have the same central angle of 145 degrees. Alright, so the measure of those arcs will be congruent. And then big one on number 8. This has a radius of 5. This has a radius of 4. These circles are not congruent. In order to be congruent, they must have the same radius. So you can now say that the measure of arc MN is not going to be equal to the measure of arc PQ. So these are not congruent. Alright, so R1 is 5, R2 is 4, so not the same circles. Alright, and then the last one, and again we'll go back to these slides in a minute, similar circles theorem. All circles are similar, right? So all, you can't say that for rectangles. You can say that for squares. All squares are similar, and you can say that for circles as well. Alright, so let's take a look at an example. Actually, there's no examples, but if you draw a circle with radius r, well, you could get another circle of n times r just by multiplying r by any factor, and then these circles will always be proportional to one another. Alright, so I'm going to pause and take some questions at this point.